Hello, and welcome to Summarize Science. Today, we're looking at a huge step forward for solar power, Perovskite solar cells. These are incredibly promising because they're efficient and cheap to make, but perfecting them requires looking at their structure on a microscopic level. The problem is, analyzing these microscope images by hand is extremely slow, tedious, and can be subjective. To solve this, researchers have created an artificial intelligence framework they call PerovSegNet. Think of it as a highly trained expert that can instantly look at a microscopic image and perfectly identify all the different components, like the main perovskite material, any leftover chemicals, and even tiny defects. This whole process, from taking an image to getting a full analysis, is outlined here. It automates a process that used to take scientists countless hours. To teach their AI, the team first had to create a high-quality dataset of over 10,000 annotated images. They used a technique called UMIP to confirm that the different materials in the images, like perovskite and lead iodide, were distinct enough for the AI to learn to separate them. This visualization shows clear clusters for each material, proving the data was good enough for training a precise model. PerovSegNet is based on a powerful AI architecture called YLO-V8, but the researchers gave it two major upgrades. They added custom modules named ASDCB and SAD, which is a bit of a mouthful, but their function is brilliant. Essentially, these upgrades allow the AI to see both the fine-grained details, like the edges of a crystal, and the large-scale structures simultaneously. This dual-focus approach is what makes it so much better at understanding these complex images. So, how well does it work? The results show that PerovSegNet significantly outperforms other advanced AI models designed for this kind of task. As you can see in this table, it achieved a higher accuracy score while being much more computationally efficient, meaning it's faster and requires less processing power. The visual difference is stunning. Here you can see the results from older models, which often miss small defects or blur the lines between materials. But the bottom image shows PerovSegNet's output with clean boundaries and far fewer missed details, especially in the tricky defect regions. But here's the most exciting part. The AI doesn't just identify things, it produces data that can predict a solar cell's performance. This heat map shows a strong correlation between the amount of good perovskite area, seen here in red, and the cell's power conversion efficiency, or PC. It also shows that as the number of defects goes up, the efficiency goes down, which confirms what scientists suspected. So, let's recap what this all means. Researchers have created an AI tool that is faster, more accurate, and more efficient at analyzing the building blocks of next-generation solar cells. This tool forges a direct link between the material's microscopic quality and its final performance. For the future, this is a game-changer. It could dramatically accelerate the research and development of even better solar materials. It could also be used for real-time quality control in manufacturing, helping to mass-produce highly efficient perovskite solar panels and make clean energy more affordable for everyone.